Okay, hello APC Mechanics students in Unit 1, Class 1, and let's start with the following section, which is kinematics. So basically, kinematics is a branch of mechanics concerned with the motion of an object without reference to the forces which cause the motion. Now basically, if we consider mechanics is a very wide branch. Now here, in this section, which is kinematics, or in this unit, basically we're gonna study the evolution of the system without referring to the cause, which is basically the force. Now, in order to do so, we need to introduce the variables of motion given by the position, displacement, distance, speed, velocity, and acceleration. Now, if you consider the displacement and the distance, one might think that these two are the same. However, at this point, we can differentiate between them, and in order to do so, we need to divide the following quantities, which are the variables of motion, into scalars and vectors. Then basically, what's the difference between scalars and vectors? Scalars is just the magnitude, and that is a number. And for vectors encode more information given by a number plus a direction. Now the scalars are given by the distance and the speed, whereas the vectors are given by the displacement, velocity, and acceleration. Now if you're asking yourself, where does the position fit into this differentiation? Basically, position is a vector. Now, what about the difference between distance and displacement? Now, let me define the distance. The distance is the measurement of the actual path followed by a moving object. It is a scalar quantity denoted by d, and the SI unit of distance is meter. However, the displacement is a vector having both magnitude and direction. Now, it is defined as the difference between the final and the initial position denoted by x. The SI unit is meter. One of the ways in order to determine the direction of the displacement vector is using the tail to head method that I will refer in the following example. Now the displacement is given by delta x, which is the final position minus the initial position. Now the Greek letter, which is the triangle known as delta. Now if delta is followed by x, that would be the final position minus the initial position. If delta is followed by t, that stands for time, that would be the final time minus the initial time. Alright, an object starts at A and it moves to B, then we're going from A to B, then to C. They're asking us for the distance and the displacement. Remember that the distance is the measurement of the actual path. Going from A to B, that would be 5 meters. And going from B to C, that would be another 5 meters. So the distance in this case, that would be 10 meters. Now, for the displacement, we need to refer to the following definition, which is delta x, the final position, minus the initial position. Now, going from A to C, independent of the path, whether we went from A to C directly or A to B to C, we're looking just at the final and the initial position. The final position is given by C, so that would be xc, and the initial position is given by A. The difference between C and A in this case is 5 meters, but notice that the displacement is a vector quantity. We need to associate a direction. The direction is determined using tail to head method. For that, if A is the starting point, then that would be the tail, and if C is the ending point, that would be the head, and in this case the direction would be from A to C. Then the distance is given by 10 meters and the displacement would be given by 5 meters, but the direction would be from A to C to the right. Now alternatively, if we consider starting from A, moving to B, to C, and back again to A. So our starting point is A, then we're gonna go to B, B to C, and then C back to A. Now what would it be, the distance? It would be 5 plus 5 plus 5, which is 15 meters. And basically the displacement given by delta x, final position minus initial position. The final position is A, and the initial position is A, so basically the displacement would be 0 in this case. And at this point we start to differentiate between what is distance and displacement. Then the distance is 15 meters, the displacement is given by 0. Now what about the direction? Always with 0 we associate no direction. Now section number 3, the velocity and the acceleration. The velocity is a vector representing how fast an object is moving in a specific direction. This is important. The SI unit of the velocity is given by meter per second, and the magnitude is known as the speed. So remember that velocity is a vector. It has both magnitude and direction. Usually the magnitude is known as the speed. So for this reason, vectors encode more information than scalars. Now, this is a very important statement. We're saying here that the direction of motion is determined by the direction of the velocity. We're gonna refer to this often in this unit. Now, the acceleration vector A is a vector representing the variation of the velocity over time. So basically, this is the definition of the acceleration. And the SI unit of the acceleration is meter per second square. Now, this also can be written as meter second to the power of minus 2 or meter per second. Now, a convenient way to picture velocity and acceleration, for this reason I've represented them in the same section, is to understand that the acceleration is a vector generating the velocity. So basically who's the vector responsible for generating the velocity is the acceleration. Let's consider the following example. Suppose here at this point, at the starting point, we have an object which is initially at rest, so the initial velocity is 0, and is submitted to constant acceleration. We're gonna notice that this vector, which is the acceleration, will start to produce velocity in the same direction. So at different instants, we're gonna see that the velocity is increasing due to the generation of the velocity from the acceleration vector. And here we notice that as time evolves, the acceleration generates velocity. And this is a very important statement. If velocity and acceleration have the same direction, which means that the object is speeding up. Okay. Now let's consider an alternative example where the object here is starting with an initial velocity given by this vector. However, now we have turned on an acceleration, but the thing is that it is an opposite direction. So what we're gonna see is that this acceleration factor will start to break down the velocity vector until the object momentarily becomes at the point 4 at rest. So we say that as time evolves, the acceleration starts to break down the velocity. And important thing to note here, that if the velocity and the acceleration have opposite directions, then this means that the object is slowing down. If an object is thrown upward with an initial velocity, it starts to decelerates until coming momentarily to rest. Then it starts to accelerate downward. This happens under the influence of gravity. Suppose that at this point, we're standing here and we launch an object with an initial velocity upward. So along the upward motion, we're gonna notice that the velocity is decreasing due to the breaking down, or because the acceleration vector is breaking down the velocity. Why the acceleration is downward? Because we know that gravity is pointing downward, so gravity is producing acceleration downward. For this reason, the velocity along the upward motion will start to break down until momentarily at this point breaks or reaches 0, while during the downward motion the velocity will be in the same direction of A, and in this case we're gonna say that the acceleration factor A is generating the velocity back downward. Now section 4, which is the equations of motion. Now at this moment we cannot introduce any equation unless we specify the type of motion. Now let me explain the following diagram because it's gonna appear later in the following slides. Now in order to to discuss the equations, we need to introduce the oriented axis. So this is the negative direction denoted by x prime. This is the positive direction denoted by x. That would be the origin. Initially, which is the car, is given by here. And we measure the initial position from the origin. Now x0 would be the initial position. After time evolves, the car is gonna move in the positive direction and the final position is denoted by x. Now we need to correlate x and x0 using the variables of motion that we introduced previously given by the speed, for example, velocity, acceleration. And this can be done if and only if we know the type of motion. So the first type of motion that we can talk about is uniform motion. And by uniform motion, what does it mean? An object is said to be moving in uniform motion if the velocity is constant, which means the acceleration is zero. So in this case, the object is moving at a steady state or at a constant rate. For example, if the velocity is 3 meters per second, we have no acceleration. The car in each second is gonna cover 3 meters. And in this case, the equation of motion is given by x is x0 plus vxt. Now, I will explain this in the following slide. And in this case, we can write down the displacement as, now moving x0 to the other side, that would be x minus x0, which is vxt. And that would be delta x is given by vxt. Now here, let me also talk about the trajectory. We are assuming that the car is moving along a certain direction, then a specific direction, then the trajectory in this case is a straight line. And let me say that the trajectory is the path followed by a moving object. Now, if we take a closer look at the equation that we have introduced in the uniform motion, x would be the final position after a certain time lapse, x0 would be the initial position. Now this linear term, t is for time, and vx would be the velocity along the x direction. For this reason, it carries the subscript x. Now, another intuitive type of motion, what about if the object has acceleration, and this is known as uniform varied motion. The word here, uniform, refers to the fact that the acceleration is constant. Now, for example, if the acceleration is given by 2 meters per second square, then this is a perfect example on uniform varied motion. However, if the acceleration is introduced as 2 multiplied by t, and t would be time, for example, in the first second, the acceleration would be given by 2 meters per second square. In the second second, the acceleration would be given by 4 meters per second square. And in this case, the acceleration is not constant, it's varying. So this is not a good example on uniform varied motion. Then let me repeat and say an object is said to be moving in uniform varied motion if the acceleration is constant. In this case, the equations of motion are given by the following. And we can introduce the displacement from this equation to be delta x. If you move x0 to the other side, that would be vx0t plus half axt square. Now, what about the trajectory? In this case, also we're talking about the path followed by an object to be a straight line. Now here we have two cases, or let me say at the beginning, v and a are parallel. They might have the same direction or opposite direction. If v and a have the same direction, as we stated previously, that means that the object is speeding up, because in this case the acceleration would be generating the velocity. However, if v and a have opposite direction, it means that the object is slowing down because the acceleration is breaking down the velocity. And an important thing also to mention that the object changes direction if the velocity momentarily becomes zero. So in such type of motions, the object cannot change the direction until the velocity vanishes. Alright? Now, also I need to mention something, that the acceleration is a vector quantity. It has both magnitude and direction. Usually this has no specific name. We refer to it as the magnitude of the acceleration. In the case of the velocity, we say that the magnitude of the velocity is the speed. But here we cannot do an analogy. there is no term for the magnitude of the acceleration. The acceleration can vary in two ways, either in magnitude or in direction. Here, because the motion is along a straight line, we suppose that the direction of the acceleration won't change. However, if we're talking about more complicated cases like circular motion, we're gonna see that velocity might arise due to the variation of the direction, but now we are concerned about the variation of the magnitude. Now let's take a look at the following equation of motion, which is stated here. And we name this equation to be the position time equation, because simply it relates the final position to the time. So x would be the final position after a time lapse t, x0 would be the initial position. The linear term is correlated with the initial velocity. Vx0 would be the initial velocity, ax would be the acceleration, and this is set to be a quadratic term because t is raised to the power 2. Now going on to the first equation of motion, and this is set to be the velocity time equation because it relates the velocity to the time. That would be the linear term correlated with acceleration. That would be the initial velocity, and Vx would be the final velocity after a time lapse t, because we know that under the influence of gravity the velocity is changing. Now what about the velocity displacement equation? This equation relates the final velocity with the initial velocity along with the term given by the displacement multiplied by the acceleration. Also, another equation that we can add, the displacement can be calculated simply from the final velocity and the initial velocity. And we know that here we have a set of equations, so one can pose the following question: how do I know which equation I'm gonna use in the problem? This depends on the given and what is asked from us. Now here there is an alert sign saying that these equations of motion are tested and can be used if and only if the acceleration is constant or zero. In the case of where the acceleration is varying, we cannot use these equations, and this need a calculus approach, as we shall see later. Alright, so one of the tasks that you should do is to compare these equations with the equation sheet that you have on your paper exam, and to compare whether these equations are given or no. Now let's consider the following exercise as an exit ticket for this class. Now starting from rest, a cart moves to the right in a straight line along a track. Then the trajectory is a straight line. The motion of the cart is represented by the dots shown recorded at equal time intervals. Which of the following best represent the acceleration vector at the beginning, middle, and at the end of the motion? Then here we have an object moving toward this direction to the right, and the position of the object for equal time intervals is being represented by a dot. From the separation distance of the dots, we need to determine the direction of the acceleration. Now if we consider the following set, we'll notice that the distance between the sets is increasing as time evolves. This means it's speeding up, which means that the acceleration will be pointing toward the direction of motion to the right. Now for the following dots, we notice that the separation distance is almost the same, which means that there is no acceleration, that the acceleration vector would be zero. Velocity is neither being generated nor destroyed. Now if we consider the following set of dots, we notice that the distance between the dots is decreasing, which means that the acceleration is breaking down the velocity and it's acting in an opposite direction of motion. Now accordingly the correct answer would be B. So thank you for watching and see you soon in a new one.